Hello, in this video, I would like to present the Java interface of the line signature scheme BlazePlus and how to use it correctly with the help of the static analysis provided in CogniCrypt. This blind signature scheme is based on lattices and is quantum resistant. It was developed and implemented in project P1 in the second phase of crossing. Please find the link to the original paper in the description of the video. As you may know, BlazePlus is a signature scheme which provides three functionality. The first method is keygen, which produces a pair of public key and secret key based on a random seed as input. The second method is sign, which needs a private key and public key produced by keygen as well as an input message. It produces a signature corresponding to the input message. The third method is verifying, which needs the public key, a message, and its corresponding signature. It then returns whether the signature is valid or invalid for the corresponding message. To use the Java interface of BlazePlus, we need to make the BlazePlus provider available to the Java Security Manager by creating a BlazePlus provider instance and adding it to the Java Security Manager. So the BlazePlus provider encapsulates all functionality BlazePlus provides. Now let's move on to see how to use the key generator to generate keys which can be used by BlazePlus. So in the first step, we want to create a key generator instance called keygen by calling the static factory method getInstant on the keyPair generator class. We provide the string BlazePlus as an argument to this method. In fact, our class BlazePlus keyPair generator extends the base class keyPair generator and produces public key and private key as bi-arrays which can be consumed by the signing and verifying algorithm in BlazePlus. In the second step, we need to provide the keyPair generator a random seed which should be generated by a cryptographic random generator. Therefore, we can straightforwardly use the pseudo-random generator as a one PING provided by the security provider Sun. Now we have created an secure random object. Next, we have to initialize the BlazePlus keyPair generator by running the method initialize with two parameters. The first one specifying the length of the random seed the secure random object given as the second parameter produces. In this case, we intend to generate a seed of length 128 bits. The last step is to generate the key pair for BlazePlus by calling generate key pair on the keygen object we created from the line 23. On KP, we can call two getter methods getPrivate or getPublic to get the private key and public key correspondingly. As we are programming using the Eclipse IDE with CogniCrypt installed, as you can see, three buttons over here. To that end, we have written a set of tries-else rules you can find in these two files. Now, as we click on the third button to start the static analysis, CogniCrypt is now running for short. CogniCrypt shows an error, which tells us that the length of the seed has to be 256. In fact, in our implementation, we require the sign of the seed in bits to be 256, and 128 in this case turns out to be a wrong parameter. Now we run the CogniCrypt static analysis again. Finally, it shows no errors, indicating that the shortcode is written properly to the crash-else rule we have written. This should conclude the first part showing the usage of the keygen method. In the second part of this video, I would like to show you how the signing in BlazePlus works. Firstly, we need to declare an object of type BlazePlus signature. As the signing process in BlazePlus encapsulates an interactive protocol between a signer and an user, it needs private key and also the public key, which are generated by the BlazePlus key pair generator we have seen previously. Next, we signal BlazePlus that we want to sign by calling init BlazePlus sign, and we pass the private key into this function. So now let's imagine the message we want to sign is a long text which is read in from a byte stream. So after a certain amount of time, we get a chunk of message from the byte stream. We demonstrate that by declaring two chunks of message as two string variables, first chunk and second chunk. We can convert a string object into a bind array by calling the method getBinds. And let's use two variables named byArray1 and byArray2 to store the byte arrays we get from first chunk and second chunk. Now we feed the object for signing we've created of type BlazePlus signature, the first chunk, by calling the method BlazePlus update. This method accepts input at a byte array. So we pass in the byte array stored in byte array 1 and byte array 2 by calling BlazePlus update twice. Basically, we can keep calling BlazePlus update until nothing is left in the input stream, indicating that we get everything we want to sign. Now, the last step is to sign the message by calling BlazePlus sign. This method produces an output byte array we name first signature, which represents the signature corresponding with the input message. Now let's see if we missed something by running the CogniCrypt static analyzer. Again, this runs for short. Now we good. It finishes. So there is an error shown here. Actually, CogniCrypt tells us that a call to initialize is missing. It makes sense because, as I explained a moment before, the signing process in BlazePlus requires not only the private key but also the public key. So now we have to initialize the BlazePlus signature object by calling initialize and pass the public key in as parameter before we sign. Now we run the CogniCrypt static analyzer again. It finished, and the error marker is gone, indicating that we fixed the error, and we get a functional code for signing. In fact, after the call to sign, the internal state of BlazePlus signature object is reset to the state after initialization. It allows us to use the object to sign multiple messages with the same public key and private key we provided. We again declare a second message and convert it to a byte array. We name byte array 3. So we can move on and sign the second message with the same object we created by calling update first, and it is followed by a call to sign. This produces the second signature. We run CogniCrypt again. Now it finishes. So it's fine. No error marker is shown. So this concludes the second part of the video, showing the signing process. In the third part, we will talk about the verifying process in BlazePlus. Again, we create another object of type BlazePlus signature. Now we name it object for verifying to distinguish it to the object we created for signing. To verify a signature associated with a message, we provide BlazePlus verify algorithm, the public key. So now again, by calling the method initialize, to which we pass the public key as a parameter. Now, as we want to verify the first signature, we simply call BlazePlus verify with the signature we created in the previous part of the video as a parameter. This method returns a Boolean value indicating whether the signature provided is valid or not. I print some messages out depending on the value of the output. Okay, here I copy some code I have prepared. As you know, with CogniCrypt, we can check if we did everything correctly by running the CogniCrypt static analyzer. Now CogniCrypt runs, it finishes. In the background, so it checked for any misusage of the BlazePlus API with regard to the else rules we provided for this verifying process. Now we see an error marker here. It tells us that a call either to init BlazePlus sign or to BlazePlus update is expected. As we have seen in the previous part of the video, a call to init BlazePlus sign, which follows a call to initialize, is necessary if we want to sign a message. In this case, we want to verify a signature, and it makes sense to call BlazePlus update to provide the BlazePlus verify algorithm, the message corresponding to the signature. Otherwise, verifying a signature without an associated message is meaningless. Now we provide BlazePlus the same message as the one we used before for signing by calling BlazePlus update twice to read two chunks of the message into the buffer of the object for verifying. Now we run the CogniCrypt static analysis again. It finishes and shows no error, meaning that our code follows the guideline the domain expert specified through the cry-else rules. As you may expect, the internal state of the object for verifying. In this case, the input buffer is reset after a call to the BlazePlus verify method. So this allows us to reuse the same object created for verifying to verify multiple pairs of signatures and messages. And to demonstrate this functionality, we use the object for verifying to verify the second signature. Firstly, we fill the input buffer of the object for verifying with the second message in the form of a byte-array, as we have seen before. Then we call BlazePlus verifying given the second signature. We also add some printout messages to make sure that everything works correctly. So now, to run the demo code, we firstly have to compile the Java code into Java bytecode by running this command. Then we run the Java bytecode with this command. So we enable GenIn and have all required shell library in this environment variable. It shows that two signatures are created and verified correctly. And it concludes my demo video showing the correct usage of the BlazePlus Java API with the help of the CogniCrypt static analysis. Thank you for watching.